Hi, I'm Shriya, and today we'll be covering 10.3 of the gas laws unit, which is relatively simple but will help you with a lot of the conceptual and the different types of math problems you may encounter in this unit. So first we need to understand what the gas laws tell us. There are basically four different equations that explain the different relationships between these four variables. And the variables we're looking at are T, which is temperature, P, which is pressure, N, which is the amount of gas in moles, and V, which is volume. Now one concept that's really important to understand, that the book sort of only goes over in the last chapter, is what factors actually determine or measure pressure. And when talking about pressure, it's all about collisions, both in terms of the frequency, like how often the molecules are colliding with the walls of the container, and the energy with which these collisions are happening. And this definition can better help you understand the following two gas laws that we're going to be talking about, which are Boyle's law and the Gay-Lussac law. So Boyle's law explains the relationship between volume and pressure. So if PV equals PV, then as pressure, for example, increases on one side, then the volume on that side is going to need to decrease to equal the other side. Which means that they're inversely proportional. So this probably makes sense, but for me, I don't know, I get confused, so I like visualizing this way, to understand why it works. So you can see here, on the left, that by increasing the volume, remembering what defines pressure is in terms of the collisions, the molecules have more space to move around, and therefore they're colliding less, which leads to decreased pressure. And vice versa on the right, when we decrease the volume, increase the pressure. And we need to remember that all of this is happening under fixed N, number of moles, under constant temperature. So Gay-Lussac's law explains the relationship between pressure and temperature. Now this one isn't in the book, but in this case, if you have P divided by T equals P divided by T, then in this case, let's say you increase the temperature, then to equal the other side, the pressure is also going to need to increase. And this is exactly the opposite of what we saw with Boyle's law, so it's going to be directly proportional, like the other two laws we're going to see. And this makes sense in this case with the temperature, because the more kinetic energy the particles have coming from increased temperature, the more collisions of greater energy are going to occur, which is going to lead to increased pressure, and then again vice versa on the other side. And this time, again, we're assuming fixed number of moles under constant temperature. So Charles's law, again, directly proportional, meaning that the temperature, as the temperature increases, so does the volume, because the molecules expand farther from each other as they get heated up and require more space. This one can actually be confusing in terms of how it works the other way around, because if you increase or decrease volume, it's not going to directly change the temperature because it has nothing to do with the actual heat source. But basically, what it's trying to say is that when the volume increases, we can assume that it must have been due to an increase in temperature, which is the same thinking you can apply to other laws as well. When you see you're in a place where the relationship between the two variables is in the equation, but you're not really seeing how it works a certain way around. Okay, so finally Avogadro's law. It's really simple, common sense, but basically the more moles or amount of substance you have, it's obviously going to take up more space, and vice versa. And in this case we're assuming fixed pressure under constant temperature. So now these four laws combine into what we call the combined gas law equation. And so in this case we have it's including Avogadro's law, but usually you're just going to see the PV and T. And that's the one you're usually using to solve math problems like this one. So it says here, an inflated balloon has a volume of 6 liters at sea level, 1 atm, and is allowed to ascend until the pressure is 0.45 atm. During ascent, the temperature of the gas falls from 22 degrees Celsius to negative 21 degrees Celsius. Calculate the volume of the balloon at its final altitude. So the first thing you're going to look at when you're given a problem like this is the units of the numbers you're given. So here we have liters, ATM, and Celsius, which are, we know, the volume, temperature, and pressure. And so that means we're going to be using the combined gas law. So I would recommend for anything, do your conversions and make sure you have units that agree. So in this case, the conversion you're going to have to make at this point is go from Celsius to Kelvin, which you should know how to do at this point or else you're a failure. I'm kidding. But yeah, so your 22 degrees Celsius is going to become at 295 degrees Kelvin, and your negative 21 degrees Celsius is going to become 252 degrees Kelvin. Now we know that we're solving for V2, so we are going to plug in the rest of our values, making sure we know which ones we're starting our initial and which ones are our finals. And then it's just algebra. Again, we're solving for V2, so what we're going to do, we're going to solve the left side, multiply by 252 to get that out of the terminator, then divide by 0.45, and if you tried it, X, you should get to be 11 liters. Okay, so this problem is a little more conceptual. So just let's try and think about it for a bit. So Sally is taking a hike, but only drinks hot water. She brings a burner with her wherever she goes so she can heat up her water until it's boiling. At the start of her hike up Mount Everest, she sets up her boiling apparatus, and finally her hot water boils. At the end of the hike, she does the same, but her water boils a lot quicker. Assuming no differences in temperature outside, from the difference between the base of the mountain and the top, or the amount of water that she's using, why does Sally's water get prepared quicker the second time? Okay, so I'll tell you that you can apply one of the gas laws to this problem, but which one do you think it's gonna be? Well, just like we did last time with the math problem, let's see what variables we're trying to compare. So we know we're talking about temperature because of the boiling point, but we know we are under constant number of moles, which also means volume. However, we're not told anything about constant pressure, and the other factor we're given here is the difference in altitude. And we know the closer to sea level we are, we're going to have closer to 1 atm of pressure. But the higher we go, the less molecules are going to be like pushing down or exerting pressure. So there we go. We know that we're dealing with temperature and pressure, which means, if we go back, that would mean Gay-Lussac's law. Sorry. Okay. So, I think earlier I accidentally said that we're under constant moles and temperature for both Boyle's law and Gay-Lussac's law, but I meant to say that we're under constant volume and moles here. Remember, whatever two variables you're comparing, the other two are going to need to be constant out of the four that we initially talked about. So coming back, we know that with Gay-Lussac's law, as pressure increases, so does temperature, which in this case we're applying to boiling point. You can see the lower we are on the mountain, the closer to sea level, the more pressure we're going to have, and therefore the higher the boiling point is. Here, water boils at 100 degrees Celsius at sea level, but we can see at the top of the mountain, it boils at 71 degrees Celsius. So, because at the top, we're going to have less sort of pushing down on the water, meaning it's going to boil and like evaporate more easily. So that is a good application of the gas law to like a real world situation, and doing this like with kind of like all the gas laws will help you understand which equation to use at which time better. So hopefully this all helped. Bye.